Hello everyone, welcome back to another video for the series. I'm Inoki and today I brought an algebra problem from IMO. And I think the solution for this problem was really interesting because I tried to I tried the normal method, but what I mean by normal method is trying to define a sub 1 and continue and from there, but and somehow write our the typical thing that we all do, but it didn't turn out to be a great method. But I think the official solution was really brilliant, so that's why I wanted to share it with everyone. Okay, so first of all, we're going to redefine, or we're going to define a sub I in a different way. So let a sub 2 equal let's say maybe the b sub 1 b sub 2 over b sub 1. And I think one hint where we can why we should do this is because notice that our sequence started from a sub 2 instead of a sub 1, and this will clear things out. So let's define a sub 3 to be b sub 2. Now notice that these two are not dependent on each other, because even though we share a b sub 2, b sub 3 can change everything. And similarly, a sub n minus 1 is equal to b sub n minus 2 over b sub n minus 1, and a sub n equals b sub n minus 1 over, it should be b sub n. However, notice that when we multiply them, everything, then we will notice that, so we can telescope them, and we will notice that b sub n is equal to b sub 1. So I'll just write b sub 1 here. They're just equal to each other. So it's totally fine if we say b sub n, but if we actually multiply things out, we notice that this is equal to 1, so that's why b sub 1 is equal to b sub n. So I will just write b sub 1 here, because I think that's a little more cleaner way to write instead of b sub n. Now then, rewriting our things here, we have 1 plus b sub 2 over b sub 1 squared I don't know why, but it's always hard to write. In here, I think it's just that I'm not quite used to it yet. I should be familiar with this, but okay. So here, let's multiply b sub 1 2 times, b sub 2 3 times, just to make our product look more clean. Dot until we have b sub n minus 1 plus b sub n, and notice that this is greater than or equal to n times because wait, n minus 1 positive numbers. Yeah. So a sub I is a positive number, and naturally b sub something. Here, assume that b sub I is greater than 0, because there's nothing wrong with that. Nothing wrong with doing that. Otherwise, we should say that they are all less than 0, but I mean, why would we do that? We can just do this. So we know that this is greater than or equal to b sub 1 squared, b sub 2 cubed, dot dot dot, b sub n minus 1 to the power of n. Now here, let's use AMGM inequality. So from here, we know that this is, so b sub 1 plus b sub 2 is greater than or equal to 2 times square roots of, but notice that we're going to square them. So rewriting them, we have b sub 1 plus b sub 2 squared greater than or equal to 2 squared times b sub 1 b sub 2. And for b sub 2 plus b sub 3, let's rewrite this, like let's split them. And why not b sub 3? I mean, why not? We can just use b sub 2. Maybe because we might have to split b sub 3 later. So using AMGM inequality, we have 3 cubed, and I'll multiply this term, so we have times b sub 2 times b sub 2 times b sub 3, and all the way up until we have plus b sub n to the power of n minus 1 over b sub n minus 1 plus dot 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 plus n minus 1 over b sub n minus 1. And there are n minus 1 of these numbers, obviously. So this is greater than or equal to, how many numbers are there? N minus 1 and one more, so n to the power of n, and times n minus 1 over b n minus 1 times b sub n. This is true by AMGM inequality, and let's multiply all of them. So if we multiply them, we will obviously have this thing, so b sub 1 plus b sub 2 squared, b sub 2 plus b sub 3 cubed, this thing greater than or equal to 2 squared, b sub 1 b sub 2, 3 cubed times b sub 2, all the way up till n to the power of n times n minus 1 b sub n. Now let's simplify this. Notice that we will have two 2's in here, which will cancel this one. And notice that for the next one, we'll have 3 3's. And that's because if we split b sub 3 into 3, then we will have 3. And by induction, we will notice that every number except for n to the power of n will be cancelled. So these all cancels. This one too. But this one survives because there's no term that can simplify that. I mean, can cross that out. So this is equal to, oh, why did I write b sub n? It's b sub 1. But there's nothing wrong with it. We just know that they're equal to each other. But for clarity, we have n to the power of n. We have b sub 1. Wait. Yeah, so we have n to the power of n, b sub 1 squared, b sub 2 cubed, b sub 3 4, all the way until b sub n minus 1 to the power of n. And that's because we have n minus 1 b b sub n minus 1. However, we also have another b sub n minus 1 in our previous I would say like group. So we know that this is true by AMGM inequality. However, notice that for the equality to satisfy, we should have b sub 1 equals b sub 2, and b sub 2 over 2 equals b sub 3, and b sub n minus 1 over n minus 1 equals b sub 1. Now let's rewrite them. So we have b sub 1, b sub 2 equals 2 times b sub 3 equals, and notice that the next one should be, because we will divide the next one into 3, we have 3 b sub 4, and by induction, like using inductive idea, we should have wait huh oh sorry. So now I'll just write them one more time. Okay. Equals b sub 2 equals 2 times b sub 3, b sub 3 equals 3 times b sub 4, b sub n minus 1 equals n minus 1 times b sub 1. So we know that b sub 1 so these all must be true. Equals b sub 2 equals 2 times b sub 3, and this is equal to 2 times 3 times b sub 4. This is equal to 2 times 3 times 4 times b sub 5, and all the way until 2 times 3 times 4 times ... times n minus 1 and b sub 1, which means b sub 1 equals n minus 1 factorial b sub 1. And notice that because b sub 1 must be greater than 0, is greater than 0 by definition, we have n minus 1 equals 1. Therefore, n equals 0 or 2. Oh, 1 or 2. N equals 2. However, because n is greater than 3, I will just write them. Because the equality does not so if n is equal to 1 or n equals 2, the equality might satisfy. However, if it's not, then no. Then yeah, so okay, then because the steps are reversible, and that proves our inequality. So what I mean by that is because let's look at our last two. We know that by AMGM inequality, this inequality is true. So this one and this one. If we just use our definition right here. But we know that the equality does not work, which means this inequality is strict instead of equal to, greater than or equal to. Now let's divide like the terms on both sides. So we just proved that this is true. Now dividing them, we get this, and reversing, we get this one. So that kind of cleared things up and proves our inequality. I think obviously our kick here is noticing this one. This is just so smart, and the thing about this problem is that everything just matches so perfectly. So like b sub 1, but it's started from a sub 2 so that we can have b sub 1. and then like using AMGM here, and then after using AMGM, we have n greater than or equal to 3. So the problem maker knew that we should also consider the equality condition and gave us this one. So it's just amazing, so beautiful. Yes. And also the reason why we should always do this is because I heard that if we don't check if we don't check for this one, then we might actually get points off for that. So we actually need to prove that our inequality is strict, if and only if, or just if we proved it for greater than or equal to. Then thank you so much for watching this video, and I will see you tomorrow. Thank you and bye.